Welcome back. Adjunct Associate Professor Max Zanin is the Managing Director of MZ Minerals and a Chief Investigator in the PRIF Mining Consortium. Max is a mineral processing engineer with a consolidated academic career. Through his dual role of being the Managing Director of MZ Minerals Consulting and being an Adjunct Associate Professor at the Universities of Adelaide and South Australia, Max has developed high international recognition amongst the global mining industry as a flotation expert. Max is an author and co-author of more than 100 scientific papers, including book chapters, referred journal articles and conference proceedings. He's also on the board of reviewers for Minerals Engineering and the Australian Research Council, and is on the technical committee of the International Minerals Processing Congress and ProSmin. Max has years of experience in technology transfer and applied research for the mining industry. Amongst his achievements, he was a project manager and chief investigator in the Amira P260 project on minerals flotation for 12 years. In the P260 project's 25-year lifetime, it had a delivered return leverage of more than 22 to 1. Welcome, Max.
Well, thank you for the introduction, Ruth, and I'm glad I'm the first one in the afternoon after lunch, because we are all refreshed, and so maybe you'll find a little bit more interesting what I have to say. So, flotation. So, this morning we've been through the entire value chain, from blasting the ore, mining, crushing, mills, optimizing SAG mills, and now we finally get to flotation, where we actually start producing some value. All the money spent to break the ore, the energy which is being invested in the process, starts paying off because we are producing a concentrate and starting producing some value. So in preparation for the very interesting talks that the researcher will do after mine of the exciting stuff which has been done within the PRIF around flotation, I will give a little bit of an introduction to the topic, especially with respect to what are we currently sensing around flotation plants, what we should be sensing, and how do we see the flotation plant for the future, for example, where are we heading and how to get there. So the flotation plant of the future, we can imagine that the flotation plant of the future will have a lot of sensors, new sensors, positioned in different points around the concentrator. So inside the flotation cells and in different critical elements of the circuit, we will have new sensors. And this sensor will send information to the control room in real time. So we'll collect a lot of information about the process. Information will flow to the control room. And then in the control room, we will have advanced mathematics to process the data. But what do we want to see in the future concentrator? We have new sensor position able to investigate inside the flotation cell, see what's happening to particles, investigate the chemistry of the process, how collectors are adsorbent particles, they become hydrophobic, and they are transported to the concentrate. And have this information real time from inside your flotation cell, traveling to the control room, where we can process the information and adjust the operating conditions to the optimum. So that's, of course, our final goal. So how to get there? To get there, there is need for new sensors. So we need to sense parameters which currently are not properly measured. We need advanced mathematics and machine learning to achieve what I refer to as intelligent dynamic control. It's an interesting term because dynamic means real time, and intelligent because it's guided by artificial intelligence. So by a combination of new sensors and advanced mathematics, we will get to the flotation plant of the future. Now, 20 years ago, a scenario like this was science fiction. Now, we are actually not that far from that because all modern concentrators are already designed and built around this concept. But what can we do better? It's new sensors and making better use of the information collected by these sensors, so better mathematics and better data analysis. So the question is, what are... Why is people laughing? Right, okay, I have to say something. Someone may notice some resemblance between one of the wise men of flotation down there and Chris Greed. It is just a lookalike. I don't want to be sued by Chris for using his image for my own purposes in my PowerPoints. It's just a coincidence. It is a lookalike. But anyway, what should we sense in flotation? There are 3 different categories of variables which are really relevant. The first category is feed variables. So we measure the composition of the flotation feed, which could be the chemical analysis, copper grade, for example, but also solids percent in the slurry, throughput, particle size, and possibly liberation of the different minerals. Then we have process variables, where we measure the dosage of reagents, energy to the flotation cells, air flows, froth depth, and so many other things. And then some other relevant parameters, which is froth stability or characteristics of the froth, and mostly pulp chemistry, pH, EH, and DO. I put them in a different color because at the moment, yes, they are measured, but not everywhere and not in the right way, and not all the information is used properly, because we need to remember the message which is down there that the wise men of flotation tell us. Flotation is based on electrochemistry. So we need to measure electrochemistry and chemistry and have control of chemistry in order to be able to predict and control the process. We may have particle size right, we may have the most efficient control of hydrodynamics, but at the end of the day, flotation is chemistry, and we need to be able to measure chemistry. So that message should be set in stone. Flotation is based on electrochemistry. Last set of variables is equipment variables, where we measure basically, as an example, power draw, vibration, wear of mechanical parts, and so a set of sensors specifically designed to control different parts of the concentrator. So characterization of the flotation feed, process variables, so how we operate things, and equipment variables, how the equipment is performing. So sensors for equipment monitoring, I consider them the low-hanging fruit, but they are very important. Basically, they're just there to detect abnormal events. And here I have just an example. An example of a sensor for abnormal events is acoustic monitoring of cyclones. A very similar thing could be achieved, for example, with the new sensor that Difeng was presenting this morning. It can be used to do the same thing, just to detect an abnormal event. The cyclone is not performing well anymore. We need to intervene as quick as possible. So this is an example of an acoustic system which is out there, which is the Sidra cyclone track. Basically, by detecting an immediate change in the sound pressure, that means the overflow is changing. There are too many coarse particles in the overflow. We need to do something. So they are done to identify as early as possible that the equipment is not working as it should. As I said, this is just one example. There could be many other things. I want to say in my discussion today, I'm just using some existing technologies which are functional to my discussion, but it's not a comprehensive overview. There are many others, and I'm not putting one on the top of other technologies. They're just there to explain what I'm going to say. So this is one example. Sensor for equipment monitoring. Then we have sensor for feed characterization, and I have to say this is now a standard in all flotation plants. So all flotation plants have, as an example, inline chemical analysis, the OSA or MSA system, which is based on X-ray fluorescence, XRF, and give us real-time chemical composition of different flotation streams. So we know our copper grade in our feed, concentrate, tailings, and whatever is needed in a concentrator. So definitely this is in the flotation concentrator of the future, but already is in most of the current flotation plants. So nothing new there. But then we may want something more, because we know that flotation is very sensitive to particle size, and therefore very recently there has been a lot of interest in having inline and real-time particle size. And within the PRIF we have something like that as well. So a couple of examples of how this can be done. There is automatical particle size done by laser diffractometry, which is a system which is out there and marketed by Outokumpu. It's basically like having a small Malvern master sizer embedded in an instrument which can put on site. So it's based on laser scattering. It can give a continuous particle size distribution, but at the same time it requires high dilution because laser scattering works at 1% solids. So it's very critical the way you collect your sample for particle size analysis from your stream. And then there is ultrasonic attenuation. As an example, there is the instrument from Thermo, which uses a different mechanism to achieve the same thing, particle size. And there is something there. So I would say it's growing, and the flotation plant of the future will definitely be equipped with inline automatic particle size, not only for the flotation feed, but in different points of the circuit. So we will see more and more of this, and different technologies and different methodologies to achieve that. And again, I go back to Defang. There is room for improvement in this area. Then something more. Yes, we have chemical analysis, but in flotation, we actually float minerals. So we would like to know the mineral composition of our flotation streams, because we don't just want to know where copper is going, but we would like to know where chalcopyrite is going, where chalcocite is going, where pyrite is going. So we want to be able to distinguish between mineral. So we want to have inline mineral assays. And this can be achieved. There is something already around. Some concentration already have something like that in place, but it's not a standard. So I would say in the flotation plant of the future, this will be a standard. Everyone will have mineral assays. This is currently achieved, again, a couple of examples, by using near UV visible light. So to complement the XRF data of the OSA, we have UV visible, which can interpret the information and give us basically the mineralogical composition. So it can be very useful if we want to trace some specific minerals in our flotation circuit. This will definitely be a standard in the future flotation plant. But then one extra challenge. It's very important in flotation to measure liberation of mineral particles, because liberation of your value mineral will dictate your final recovery and concentrate grade. At the moment, the only standard way to do that is using QuemScan, which is very accurate, but it is offline. So it takes a couple of hours minimum, because you need to do sample preparation, put it under the instrument, have a measurement, so it doesn't give you real-time liberation. So in the future, we will definitely have real-time liberation in the flotation plant. How to get there? There is some research around. Some is promising, some is less, and I put a couple of examples because I found them very interesting to myself, to my own interest. One is using XRF in a way as if it was a digital camera, taking an XRF photo of your sample, so that each individual pixel in your photo is an XRF signal, which has a different color, so you can basically map the composition of your sample and identify different minerals and composition and liberation of the different minerals. This is, at this stage, is really far from being available, but there is research around it, and it was very interesting as a concept, as an idea. And then we have microtomography. Microtomography is already used for liberation. It has, at the moment, similar problems as the QuemScan in terms of being inline and immediately available, because if you're familiar with tomography, you need to take a lot of projections of your sample, so it takes time. You need to collect a sample, take it to a measuring chamber, take a lot of projection, and reconstruct the 3D composition of your sample. It takes a couple of hours. But there is a lot of research going on to reduce this processing time by using advanced mathematics, what is called digital algebraic reconstruction techniques, which is, it's cool. It's like what they do for images in computers. You have a bitmap, which is weighted megabytes, and you convert it to JPEG, which is few kilobytes. You can do the same with this, and use just a few projections. Instead of using 200 projections, be able to reconstruct your sample without losing quality with very few projections in a fraction of the time. And I know that at the moment, there are groups who are able to get decent results, reducing the processing time from 2 hours to 1 minute. In the future, probably it will be a few seconds, and this system may be able to become available online. And then fraud visual analysis. This is very interesting, because fraud visual analysis has been out for at least 20 years now. Every concentrator have, or used to have, they have fraud cameras, but the use which is currently done of all the information which could be collected by fraud cameras is minimum. You go to concentrators, and most of the time froth cameras are there just to detect if the cell is producing any concentrate. Is it flowing? Is it not flowing? There is something wrong. But all the useful information we could get in terms of composition of particles on the froth, bubble loading, and correlate visual analysis to concentrate grade and recovery, we are still behind because we don't use that information as well as we could. A lot of work has been done recently, and there is room for improvement in terms of using artificial intelligence to interpret the data from visual analysis and be more able to predict what's happening in the concentrator. Mezzo, for example, you're probably familiar with VisioFroth, which is considered to be the standard for visual analysis, are recently marketing a unit which is called FrothSense Plus, and they claim they use artificial intelligence and they can achieve these goals much more efficiently than in the past. But there is a lot which can be still done to improve the data analysis and what we can get out of visual analysis, because at the moment it's underutilized in most concentrators. And then we move to pulp chemistry, and inline pulp chemistry, it's been one of the targets and goals within the PRIF, because it's very important. As we said before, we need to measure pulp chemistry if we want to have the process right. And at the moment, pH, EH, and DO are some concepts that in some concentrators they have some meaning and they make use of them, in some others they don't. pH, there are probes everywhere, but maintenance is poor, they're not maintained and clean, and you need always to think that if in your plant you have your pH which is steady at target 7.5, and it's been steady at target for 2 months, doesn't mean you have control of your process. It means your probe is broken. You need to go there and check that the reading is real. So it's very interesting what Megato has been designing in the last years, which is the Mega Pulp, by which we can have a more reliable and continuous measurement of the pulp chemistry measurement, and pH, EH, and DO in the plant of the future will be a standard as a continuum measurement, and inclusion of these parameters in the data analytics and in the machine learning, because it is ultimately chemistry which dictates recovery and grade. So this information will be available online. We are not far from achieving that, and the PRIF is been helping in this space, so it's very good, and we should be proud of what we are doing in this area. And new pulp chemistry. I wanted to select just 2 of the very interesting talks which will come after mine as an example that what I strongly believe, and researchers in the PRIF believe, is that the future for sensing around flotation will improve sensing around pulp chemistry and what's related to chemistry. So you will hear from Todd, for example, that it is possible to achieve a real-time sensing for frother concentration in the system, which will be great, because then we know if what we are adding is doing what it's supposed to be doing. Maybe that can be extended to collectors, step forward, so we know if our collector is going to the mineral surfaces, or if we are just wasting money throwing in a lot of xanthate, which is doing nothing to the system. So having this real time will be a step forward, and I believe that this will be in the concentrator of the future. And again, what Linda is doing, detecting critical ions in the system. She's doing that now for leaching and detecting ferric ions, but that may find applications in flotation as well. We may be able to have a sort of fiber-optic sensor which will tell us, listen, your pyrite is getting activated and it's floating. Your chalcopyrite is oxidizing, and we can control that because we can have real-time measurement of ions in solution. So in the future, sensing of chemistry will be definitely there and stronger in the flotation plant of the future. Now, to conclude, how to get there? What's the step? Well, Adrian this morning explained this concept in a much more educated way and giving a lot of examples of how this should properly happen if all people involved are doing their part. But the bottom line to me is having an open mind for end users, because most of the time they see implementing some new technology as a disruption on their production, on their daily activities. And why do you bother me with your Canon? Because I have my flotation cell in front of me and I need to optimize it now. And the same applies to suppliers, the same applies to researchers. Having an open mind is the only way for ideas not to remain just ideas, but to slowly become something which is generating value. And I'm not taking more time on this because it was explained much better than what I'm doing now. But I guess that joke is the clear concept, and we should have that always in our minds. All right, thank you.
We have time for one question for Matt.
You'll be hearing from my lawyer.
It's all about IP, is it?
No questions? All right. Bismark Amankwaa-Kyeremeh is a PhD candidate at the Future Industries Institute at the University of South Australia. Bismark has a Bachelor of Science with honours in Mineral Engineering from the University of Mines and Technology, Ghana. During his PhD, Bismark has published 6 high-quality journal and conference articles and has 3 additional articles under review. On top of that, Bismark also got his full driver's licence last year. But did you get a cat? Bismark is planning to complete his PhD next month, and Bismark has talent and the capabilities and is looking for employment. Bismark.
Hi, everyone. Thank you, Max, for giving the overview of flotation, which will make my presentation very easy for my audience to understand. So my name, once again, is Bismark Amankwaa-Kyeremeh, and today I'll be talking about sensing and optimization of flotation and their integration with grinding. Okay. Flotation has been around for over a century now, and irrespective of its long existence, the process still is inefficient when it comes to recovery and grade. So the main objective of this project is to have an improved, stabilized, and cost-effective flotation process. And that is where my project sits with other flotation projects, and it comes right after the combination, guys. So this implies that if Kwaku does a good job, then it will be an easy job for me when it comes to flotation. So since the commencement of my project, these are the main key findings that I have. And the first one is that Gaussian process regression model can make good copper recovery and grade prediction. And the second one is that Pareto search algorithm finds the optimum operating point that will see to the maximization of copper recovery and grade. And finally, we've been able to ascertain that pulp chemistry, indeed, they are very essential when it comes to the prediction of rougher copper recovery. And these findings are useful. So just like in the world of sports, no coach would like to change his or her winning team. So likewise, on the plant, it's not advisable to play with your set parameters or set points of variables. But with the model that we have the flexibility to simulate rougher copper recovery and grade. And this will give you an idea of what to expect when you are to vary a particular variable in a range. And ultimately, the model that we have at the moment can be integrated into a model-based predictive controller. And this will help to have a process control of the system. And in model-based predictive controller, what happens is that the predictive model of the system is used to control the future behavior of the process, and they are very effective for multivariable process like flotation. So we know that fluctuations in the performance of flotation mostly emanate from the operation of the various variables at different set points. So with the optimum values that we have at the moment, we hope to have a more stabilized and robust flotation process on the plant. So this is the general methodology that we adopted. And this methodology was motivated by the availability of plant historical data and then expertise in flotation and the emergence of advanced computational techniques for solving complex problems. So we normally begin with the collection of data from the data historian of BHP Olympic Dam, and this is collected at a confidence of 100%. Owing to the transient operation that normally happens on the plant, we undergo pre-processing and standardization. And after that, we partition the data into training, validation, and testing set. So there's no general rule for the partitioning, but what you have to bear in mind is that the training data should be significantly large enough so that it captures the full characteristics of the data that you are dealing with. So from there, they are now subjected to predictive algorithms like support vector machines and artificial neural networks. And basically, these algorithms operate by, first of all, establishing a correlation matrix between the various input and output variables. And based on this correlation matrix or predictive function, it's able to make new prediction when you give it a new data. After the development of the models, we have standards that are used to assess the performance of the models. And the standard that we considered in this work included correlation coefficient, root mean square error, mean absolute percentage error, and variance accounted for. So for a good model, we expect the R values to be approaching 1. And in terms of the error statistics, that is the root mean square error and the mean absolute percentage error, we expect them to be minimum as much as possible, something approaching 0. And for the variance accounted for, we expect values close to 100% as possible. So after the assessment, based on the best performing model, we extract the predictive function of that model, and we use that model, that predictive function as the objective function for optimization. Go back. For optimization, I think there have been previous presentations that has talked about the operation of optimization algorithms, so I'm not going to talk about that here. So this is the data and study area that we considered in our work. So we collected the data mainly from the rougher circuit of BHP Olympic Dam, and specifically, we considered data from the rougher train A. We also made use of Magapop in collecting pop chemistry data in terms of pH, EH, dissolved oxygen, and temperature. So these are the main data set that we considered in our work. So this image here shows the prediction that we did with our model in terms of copper recovery and grade. And looking at the statistics, it shows that our model is actually doing a good job when it comes to the prediction of the output of the process at BHP Olympic Dam. So this work also shows we wanted to ascertain the impact of feed grade and feed particle size on the optimum values that we have. Because in as much as we have optimum operating values for the various variables, variables like feed grade and feed particle size, it's very difficult to keep them at a particular value. So we did a simulation where we varied feed grade and feed particle size simultaneously, but we kept all other variables at their optimum values as found by the various optimization algorithm. And from these results, we realized that if we are to go by this approach, we can have a near optimal recovery and grade with the values that we have at the moment. So going through literature, we realized that even though machine learning models have higher accuracy and they have very good predictive performance, however, the work that have been done so far mostly wouldn't include pop chemistry parameters. So what we did with the little data that we have on pop chemistry from BHP is that we, first of all, modeled with just plant variables. And that is the image on the left. And after that, we included the pop chemistry variables in terms of pH, EH, dissolved oxygen, and temperature. And from this slide, we can see an improvement in the performance of the model that we developed. So future recommendation is that to date, we know that pop chemistry is very essential when it comes to the prediction of the recovery of the process. However, we have very little data at hand. So we recommend that more data on pop chemistry should be collected in order to validate some of the work that we have. And also, since the Gaussian process regression model has proven itself when it comes to the prediction of the metallurgical output of flotation. We are also recommending that models should be built for the grinding circuits and the hydromet section so that overall we can have an integrated model for the plant. At this point, I would like to acknowledge my supervisors, Richmond, Bill, and Max. I would also like to acknowledge my team from BHP, that is Kati, Kavita, and Meredith. And shout out to you, Chris, and also State Government of South Australia and all stakeholders. Thank you.
Do we have a question? Kathy has a question here, yeah?
No, he's asking.
No.
Okay.
All yours.
It's just a really easy one, Bismark. That was really good simulation. The important thing to note is Olympic Dam's flotation recovery, without us trying, is very high. You saw those very high recoveries that we usually get. The question for you is how much data did you end up actually collecting? You know, with the data set that you had learned from up there? I know there's been all kinds of problems and all that, yeah.
Yeah, so for the application of machine learning models, especially for industrial application, it is advisable to consider a long span of data so that you can capture the various plant regions that happen on the plant. So for this work, we consider the 6-year period. But when it comes to the pop chemistry work that we did, we have very limited. So that went for like maximum 3 weeks.
Yeah.
So that is why we are recommending a longer period.
Yeah, yeah. Thank you. It's good stuff, though.
Thank you, Bismarck. Thank you, Nigel. Linda Rozenberga is a PhD candidate at the Future Industries Institute at the University of South Australia. And Linda is planning on completing her PhD in September. Earlier this year, Linda presented her work at the 33rd Australian Colloid and Surface Science Student Conference, where the talk received a Healy Hunter Award, recognising the most outstanding student oral presentation at the conference. Linda also successfully presented her work at the 17th Conference of the International Association of Colloid and Interface Scientists in Brisbane 3 weeks ago. When she's not working on her PhD, Linda has been discovering the beauty of South Australia through hiking and camping. And Linda's favourite spot is the Flinders Ranges. Welcome, Linda.
Hello everyone. So today I would like to tell you about my PhD project, which is on developing a new metal organic framework-based fiber optic sensor. And the goal of this project is to develop, sorry about that. Yep. Oh, there we go. So the goal of this project is to develop a sensor that can quickly and accurately measure how much iron 3 we have in leaching processes. But before we get into the science, I would like to invite you to take a minute and think about our everyday lives. Many of us have a car that we use to drive to work every day, and we rely on fuel gauge to let us know how much fuel we have left in the car. And imagine if we didn't have that. If we get in the car in the morning and we have no idea how much fuel we have, are we going to get stranded on the side of the road on our way to work, or are we going to stop at the petrol station unnecessarily and waste our precious time? Or another example, let's say you're not feeling well and your doctor asks you to do a blood test. A typical blood test would take about 3 days to get the results back. But imagine if it actually took us 3 weeks and what effect that could have on your health. So we don't want to face risk and uncertainty in our everyday lives, so why would we allow them in the key processes of the business? Now let's return to mineral leaching. It's a process where we dissolve the ore in acid or solvent to recover the valuable mineral. And it is governed by several different parameters since it's a chemical reaction. For example, pH, time, and temperature, which are fairly easy to measure and control. Others are a bit more tricky, like particle size and particularly the redox potential. So in the leaching process of copper, zinc, uranium, and gold, the redox potential is controlled by the ratio of iron 2 to iron 3 ions in this process. For example, a study done in 2001 showed that optimizing the iron 2 to iron 3 ratio in copper leaching process allowed the authors to increase the copper recovery up to 3 times. We have good, reliable methods how to measure iron 2 concentration in solutions. However, iron 3 concentration is a lot more difficult to measure. It requires extensive sample pretreatment. It needs expensive, complicated equipment. It's a long process, and a lot of times the measurement we obtain is not exact and precise because we're not determining the iron concentration directly. So, as an alternative, we are offering to develop a luminescence-based sensor. Luminescence is the ability of some materials to absorb light and then emit it at a different wavelength. And you might be familiar with these materials as glow-in-the-dark materials or glow-in-the-dark paints. Luminescence sensors are known to be very fast, accurate, and selective. So we split my project in 3 parts. And in the first part, we needed to find a chemical that would be luminescent and would respond to the presence of iron 3. Then we needed to take this material, metal organic framework, or MOF for short, and encapsulate that in a polymer matrix to hold the powder crystalline particles together in one place. And then we use this composite material to coat optical fiber and fabricate a practical sensor. So in the first stage, after we selected a potential MOF from the literature, we performed in-depth study to understand its properties and limitations. We determined new information on the MOF structure that hadn't been published before. We optimized the synthesis to increase the yield from 4% to 32%, and we also looked into why do we have a response from the MOF crystal to the presence of ferric ions. Why do we see the change in the emitted color and the intensity of the light? Then, when we encapsulated this powdered material in a polymer composite, we saw that these 2 materials have a synergetic relationship. The polymer increased the luminescence intensity, which you can see in the first graph. In red, we have the intensity of the light that is emitted by the MOF powder, versus in purple, where we have this composite material luminescence intensity. This is important because the intensity of the light is what we are using to measure how much iron we have in our solution. That also increased the sensing range of the sensor. As a powder material, this MOF senses up to 4 parts per million of iron 3, while as a composite, it could sense up to 120 parts per million. It also made the sensor reusable, and we started testing out simulated leaching conditions to see how decrease in pH and presence of other metal ions would affect the sensor. And we found out that only iron 3 causes decrease in the intensity of light emitted by our sensor. Then lastly, we developed the optical fiber coating process, and we established the prototype sensor setup. And we also further increased the sensing range. Now it's from 0.1 to 1.4 grams per liter, which is a lot closer to actual industrial processes. So if we wanted to use the sensor that we're developing, first we would have to have this sensor suspended in water cell to keep the polymer hydrated and to allow the ions to penetrate the polymer structure and interact with our MOF sensor. Then we would measure the light intensity emitted by the sensor without any iron present, and then measure again the intensity of the light with the iron present. And if we measure the ratio between these 2 intensities, we can determine exactly how much iron we had in our sample to begin with. Now, working in a laboratory is not always as exciting and fast-paced as it can be portrayed in movies and TV shows. A lot of times it's very time-consuming and repetitive process. So for example, if I was asked to analyze how much iron I have in a sample, it would take me several steps to get to the measurement process. I would need to dilute the sample, adjust the pH, remove any impurities, prepare the solution for measurement, and only then I would get to the testing point and then to the analysis to determine how much iron I had in the sample. But if we were using the sensor we're developing, we're skipping all of these steps and going straight to the analysis and determining how much iron we have. So that would not only save the time for the employees, but also would provide us with close to real-time process monitoring and precise measurement of how much iron we have in our process, which would allow us to optimize the leaching process. It would also increase the copper or other mineral recovery rates and save the money and resources for the company. However, there is more work to do. Just like historically, computers would take up entire room and they evolved into modern day laptops. The current sensor setup is rather large and bulky. We require many different parts and components to run this sensor. But with more time and funding, this could be transformed into something that is easy to use, practical, and transportable. The technology to do this already exists. We just need a bit more time and resources. And the sensor is not only potentially applicable in mineral leaching processes. Iron 3 affects, for example, drinking water quality. It can give the water unpleasant color and cause negative health effects. So we could use the sensor to control the drinking water quality. It can also potentially be used in medical and biological setting because not enough iron in the human body can cause anemia, while too much has been linked to Parkinson's and Alzheimer's disease development. And we could also use it to control the wastewater, the iron concentration in wastewater. Too much iron 3 in environment can cause the bacteria and algae growth and the death of aquatic plants and animals. So there are many different potential applications for this sensor that we are developing. So I would like to thank my university supervisors, end user partners, translation partner, and the sponsors of PRIF for enabling this interesting project. And thank you for your attention.
For Linda.
Linda, you developed just one sensor for ferric iron, or it could be used for other metals as well?
Yes, MOF materials is a whole group of chemicals, and there have been reported different materials for different potential sensing. So for example, I am aware that there are MOF materials that can be used for copper, for nickel, for lots of different metal ions, for antibiotics, for explosives as well. So using these technologies of how to encapsulate the MOF material into polymer and how to transfer it onto optical fiber could be used to fabricate a large array of different sensors.
Thank you.
Yeah, thank you.
Kirsten Louw is a PhD candidate at the Future Industries Institute at the University of South Australia. Kirsten is from South Africa and has just returned from a trip home. After completing her master's degree, Kirsten worked in banking, taught English in China, and then returned to academia in Australia. Kirsten is planning to complete her PhD in December this year. Kirsten has published 2 papers and earlier this year attended a workshop called Mathematics in Industry Study Group. Kirsten's highlight during her PRIF time has been ghost hunting at the Z ward. Kirsten.
I happen to like spooky things. Hello, everyone. So my project is right at the end of the mining process, and I happen to be the only mathematician in the group. So if you have a problem, fantastic, approach us. Approach a mathematician. We are very helpful at solving problems. We use mathematical models to describe systems, to gain further insight into a problem, and to provide answers to your questions. But don't worry, I'm not going to go into any detailed maths today. And in particular, I'm an applied mathematician, and there are many subsets to applied mathematics. And you have been introduced to a few of those subsets, namely optimization, computer science in terms of machine learning, and statistical modeling. Where I come in is with the sensor. Linda's work and my work are very closely interconnected, where Linda is creating a sensor to to detect ferric ion concentration. So this sensor is made up of an optic fiber with a MOF polymer coating. The sensor is submerged into a solution containing ferric ions. These ferric ions associate to these MOF crystals, and so when we pulse a light, send a light source through the sensor, changes in luminescence is detected and the signal is processed. And you might ask yourself, but where is the mathematics? And it is located at the sensor. So we use mathematics to understand how iron 3 interacts with these crystals and how it interacts with the sensor. And we study this in two parts. In the microenvironment, we look at how iron 3 interacts with the crystals embedded into the polymer. Because of this interaction is what influences the changes in luminescence. Then we can ask the question, how does iron 3 interact with the MOF crystals? In the macroenvironment, we study how iron 3 travels through solution and through the polymer to interact with the MOF crystals. Because if we understand this, we know how long to expose the sensor to get an accurate reading. And then we ask the question, what physical properties can optimize exposure time? Looking at the microenvironment, what we see on the left-hand side is what the crystals look like in real life. But I'm really interested in what these crystal structures look like at an atomic level. So in the middle, we have a top view of the atomic structure. And if we look at a pore, these pores have depth. So you have a column of atoms going, well, into the slide. And then we are looking at the interaction of these pores with the hydrated iron. So on your right-hand side, you have the iron in the middle, surrounded by water molecules. And we want to know how this hydrated iron interacts with the MOF crystal. There are two ways to calculate interaction energies and forces. The first one is molecular dynamics, where we look at the atom-to-atom interactions. So if we isolate a pore and we take hydrogen from the hydrated ferric ion, and we look at how does this hydrogen interact with each of the atoms in this pore. In the second approach, we use continuum mechanics, and this is the approach that I've used. So instead of looking at atom interactions, we are considering shape-to-shape interactions. So if we isolate a pore, we approximate it using a cylinder. And for the hydrated ion, we approximate it by a point and two concentric spheres. And now we can answer our question, how does iron 3 interact with the MOF crystals? We found out iron 3 is attracted to the MOF crystal, however, it's too large to fit inside the cavities. This isn't bad news. This is actually good news, because this means that we can reuse the sensor, and this is a cost saving. Some additional insights is that we found out our method is about 500 times faster than molecular dynamics and still provides reliable results. We also found that the other metal ions are attracted to this crystal, but this crystal in particular is iron 3 selective in terms of sensing. Taking a step back and looking at the macro environment, in the lab, it's a very controlled environment, so we know the concentration of iron 3 in a solution. However, when on site or at the mine, we don't know what that is. So we want to know, how does iron 3 diffuse through solution, the polymer, to interact with the crystal? This is a cross-section of the modeling environment. When we see the circles, it's iron 3, so we're looking at how iron 3 diffuses through solution, the polymer, and at the bottom we have an optic fiber. There are MOF crystals distributed throughout the polymer. However, we first consider a crystal at the solution polymer boundary. And then we can study for properties that can affect sensing time. So the diffusivity of iron 3 in solution and the polymer, and its relative sizes between the two diffusion constants, the association rate, so how quickly iron 3 binds to the crystal, and dissociation rate, how quickly iron 3 unbinds from the crystal, and then flux of iron 3 at the crystal. From these four properties, we can now answer our question. If we increase diffusivity, association rate, and decrease flux, we have a shorter exposure time. If we decrease diffusivity in the polymer, we do have shorter exposure time, but this makes for poor sensor functionality because it only decreases sensor time for crystals at the surface of the polymer. What we also found out is knowing the dissociation rate helps predict iron 3 concentration in a solution. The benefits of this is having a good sensor is reduced material and time wastage, and we gain further insight into the system. Having a mathematician alongside experiments means that there is less time wastage on experiments where you have a shorter parameter testing for different variables. I would encourage you to find a mathematician. But first, you need to highlight that you have a problem and then seek out our help. We are friendly enough. I would like to thank all of these lovely people, the state government, PRIF, and UniSA. Thank you.
Do we have a question for Kirsten?
Kathy.
What's your next little chore there? What's your next task, you know, with your mathematics? Even
My
in the project?
PhD or in life?
You choose the answer.
In my PhD, I'm going to do more mathematical investigations into the systems of equations. It's interesting for me, but I don't know if the results will be as interesting for you guys. It's going to be very math heavy. It's going to be really mathematically inclined. Yeah. So it will feed into the math space in terms of research. And after? Oh, that's a surprise to all of us.
Requires a job. Okay, one more question.
And it might be also for Linda. You mentioned that the hydrated ion particles are attracted but don't fit in the tubes. Presumably there's going to be other things in the fluid that do. So could the MOF get fouled by other species, and what would they be, and how would you deal with that?
So that's not so much of a problem because there are so many cavities, because you'll have so many MOF crystals distributed in the polymer, and there's many cavities to be filled. So we're not too worried about it being blocked by other substances, other metal ions and such. Does that answer your question? Or?
Relatively fluoresces.
Yes.
But the intensity of the fluorescence then would be related to, in our pore spaces you've got available for the ion species, correct?
Yes.
So
So the fluorescence, yes, because it's interacting with the iron 3. Or you're saying that because there's a lack of space, the iron 3 won't be able to...
yeah, fouling could still be an issue that would affect the signal, even if the MOF was still working.
Yeah. All right. We can have a discussion later.
Thank you, Kirsten. We will now have a 15-minute break for afternoon tea, a slight break in the Program B presentations, and we will return afterwards with the Chief Scientist of South Australia. So please be in your seats at 2:55. Thank you very much.